So far, whatever we have studied in last two lectures, all the circuits were your latch. And here in this slide, we are going to discuss about the difference between latch and a flip-flop. So latch is a level sensitive to control signals. Means as we are using a clock signal C for the synchronization, that means whenever C is 1, your input will be propagated. The inputs are in SR flip flop, it is SR, it may be JK, it may be D, or it may be T. So whenever clock is active, the say input signal will be propagated, and according to the output will be there at the output Qn and Qn bar. So here are the logic level 1. So we can see here directly, these are the dark places, dark spots or the dark label, which has been considered as logic level 1. So whenever we are talking about latch, so latch is always a level sensitive device. So when we come to the flip flop is an edge sensitive triggered or edge triggered. Sensitivity comes from the triggering, means we are giving a trigger pulse. So flip-flop samples the data on clock transitions. So there are two clock transitions here we can see in the circuit diagram. So there are two clock transitions. When we are going from 0 to 1, it is said to be a positive edge trigger or positive edge response. On the other hand, in the second figure C, we can see that when we are coming from 1 to 0, or there is a transition from 0 to 1 to 0, it is known as negative edge triggering or negative edge response. So whenever we are talking about that it is a level sensitive, then the device will be activated or active or triggered at either logic level 0 or logic level 1. So on the other hand, flip-flop is a S-triggered device which is triggered either on the positive edge whenever there is a transition between 0 to 1, or at the negative edge when there is a transition between 1 to 0. So this is the basic difference between flip-flop and the latch, and this topic is many times asked in your Viva or in an interview, what is the difference between latch and the flip-flop. So now come to the characteristic table of all the flip flops. What the characteristic tables are, we have discussed in the last lecture. So for the SR flip flop, where here En is the clock, that is a control signal. Whenever clock is 0, we are just summarizing all the 4 flip flops with its characteristic table or the operating table. Whenever clock is 0, whatever is the input X and R, the output has no change. Means previous state is reserved. With clock 1, if SR is 0, 0, there is no change. If SR is 0, 1, that is R is 1, S is 0, it is the condition of reset. Whenever S is 1 and R is 0, condition is set. So we define reset as output equals to 0 and set as output equals to 1. And 1, 1 condition is indeterminate and it is not allowed in SR flip-flop. Similarly, we can discuss about D flip-flop, and we have assumed that the clock is active, that is clock is 1. So whenever D is 0, output is 0. Whenever D is 1, output is 1, irrespective of the previous output. For the JK flip-flop, we are assuming that clock is active. For 0, 0, it is no change. 0, 1, that is reset, output will be 0. If J is 1, K is 0, output is set, that is Qn plus 1 or Qt plus 1 will be 1. And for the 1, 1 condition, output will be complemented. If it was 0, then the next state will be 1. If it is 1, then the next state will be 0. And this concept of JK00 and JK11 is converted into the T flip-flop, that is toggle flip-flop. And we say for the toggle flip-flop, with clock active, if T is 0, then the output is no change. If T is 1, output is complementary. So keeping in mind these 4 characteristic tables or the just operating tables, we have to find out the characteristic equation of each and every flip-flop. How will it characterize this equation will characterize the operation of the flip-flop. So let's move and let's start with the SR flip flop. The first we are going to derive the characteristic equation. So it is the block diagram of SR flip flop. We have two inputs S and R. We have a control input C, one output Q and another output Q bar. So it is assumed that Q and Q bar are in the complementary mode. We have the characteristic the operation table. So with this help, we'll find out the characteristic table of the flip flop, and the characteristic table assumes two inputs S and R and one input, that is the previous state Qn or Qt. So we have three inputs in the characteristic table. Q is the previous state, S and R. And with these three inputs, we have 8 input combinations ranging from 000 to 111. So with three inputs, 2 raised to power 3, that is the 8 combination ranging from 0 to 7. We write all the combinations all together. Then with the help of this operating table, we'll find out the value of the next state. So let us discuss how it happens. Whenever SR is 0, next state is hold, that is no change. So the SR 0, next state is no change. So Qt plus 1 will be equals to Q. With SR 1, that is reset, output will be 0. SR 10, that is set, output will be 1. And 1 condition is not allowed. So it is unknown, or we will put as it don't care. Again with 0 and Q equals to 1, next state will be Q, that is 1. 1 reset 0, 10 set 1, and 1 is an undetermined, that is the don't care condition. So this characteristic table is derived from the operating table, or the how the SR flip flop works, and that has been summarized in a characteristic table. So with this characteristic table, we have to find out the expression for Qt plus 1 or Qn plus 1. So here we draw a map for the output. So we have I have Qn and SR as the three inputs, and I have tried to plot these undetermined condition has been denoted as don't care X. So here one is quad and one is a pair. Solving this, we find Qn plus 1 equals to S plus R bar Q. So this is the characteristic table. With the help of this characteristic table, you can find out the next state whenever you are provided S, R and Q. If you are provided both inputs and the previous state, you can find out the next state directly with the help of the characteristic equation. Next, we are going to derive the excitation table of the SR flip-flop. Excitation table is the table when you know the present state and the next state of the flip-flop, and you have to find out what will be the value of the input combinations, that is S and R. So it is used when we are going to design asynchronous sequential circuits, and many types of counters when we are going to design in the next some coming lectures. So in that case, this is the case when we know the present state and the next state of the flip-flop, and we have to find out what are the input values of the S and R. So here we use the excitation table, and the excitation can directly be derived with the help of characteristic table. So it is the characteristic table of the SR flip-flop. So we find there are two combinations whenever present state is 0 and next state is 0. So directly we can see that whenever present state and next state are 0, S is constant 0 and R is going 0 and 1. So in this case, if we put present state 0 and the next state 0, then the value of S is 0 and value of R is don't care, because it is 0 one time and 1 time. Again, we find the next combination whenever Q is 0 and Qn plus 1 is 1. So the condition is that S equals to 1 and R equals to 0. Another condition is whenever present state is 1 and next state is 0. So the input combination S, R are 0 and 1. And the next combination when present state is 1 and the next state is 1, we see that S is changing 0 to 1 and R is constant 0. So I can summarize it in a table. Present state and the next state are the input, and we have to find out what were the input combination. So you see directly for the 0 0, the value of SR must be 0 and don't care. So here is the blue lines representing these conditions. With the 0 1, with the green line, when present state is 0 and next state is 1, the input combination is 1 0. For 1 0, yellow line, present state is 1, next state is 0, and the input combination is 0 1. So here is 0 1, and 1 1 present with the red line. 1 1 is represented with the red line. So in this case, S is don't care because S is changing 0 and 1, and R is constant 0. So this is the excitation table you have to use many times when you are going to design the circuits in unit 2 and unit 3. So we are frequently using these excitation tables. Similarly, for the next type of flip-flops, that is D flip-flop, we first will find out the characteristic equation, then the excitation table. Here is the block diagram of D flip-flop, input D and a clock, Q and Q bar as the output. Operation table of D flip-flop, whenever D is 0, output is 0, whenever D is 1, output is 1, irrespective of the previous state. So here is the characteristic table. So in the characteristic table, we have input D and present state. So with the two inputs, we have four possible combinations: 0 0, 0 1, 1 0, and 1 1. And the output is whenever D is 0, in two cases, output is 0 because it is stated here in the operation table. Whenever D is 1, output is 1. So I can plot it into a K map. So here is the K map, Qn and D. And the characteristic table comes to be Qn plus 1 equals to D. So the output is equals to D. That is the characteristic table, or we have seen in the operation table of the D flip flop. Similarly, we can find out the excitation table. Excitation table is drawn with the characteristic table as we have done in the last. So this is the characteristic table and excitation table. How it comes? Whenever present state is 0 and the next state is 0, there is only one combination. Then the present state is 0 and next state is 0. Then the input is 0. So input is 0, present state 0, next state 0, input is 0. Present state 0, next state 1. So the input is 1. So here input we have put it 1. Present state 1, next state 0. Input is 0. Present state 1, next state 1. Input is 1. So this is how we have derived the excitation table of the D flip flop. Now JK flip flop, block diagram of JK flip flop, J, K and clock as input, Q and Q bar as output. Its operating table: 0 0 no change, 0 1 reset, 1 0 set, and 1 1 complement. With this help, we can find out the characteristic table: 0 0 no change, 0 1 reset, 1 0 set, and 1 1 toggle. So the previous state was 0. So here the next state will be 1. It will complement the previous state. Again 0 0 store, no change, 1 is here. 0 1 reset, 1 0 set, and 1 1 toggle. So the previous state was Q was 1, so it will be 0 here. In the same manner, we will solve the K map. Here is the K map. And we find the characteristic table equation as Qn plus 1 equals to J Qn bar plus K Qn. Now we have to find out the excitation table. So in this case, you never need to just remember or just to jot down these characteristic table and the characteristic equation. The more important, you have to remember the excitation table, because you can draw the characteristic table with the help of the operation table. The main thing is you have to remember the excitation table. In the next some coming slides, I'll show you that how to remember these excitation tables. Characteristic table is drawn with the help of the operation table. What is the operation of the particular flip flop? With the help of present state and the input, you can find out the next state. That is the characteristic table, nothing else. So again, we are going to find out the excitation table of the JK flip flop, and here is the excitation table. Now let us see how this excitation table is drawn. So in the excitation table, we have present state and the next state as input, and J and K, that is the J and K as the output. So here we go. Present state is 0, next state is 0. So you can directly see that J is 0 in both cases and K is 0, changing from 0 to 1. So I have put it J equals to 0 and K equals to don't care. Next input combination must be 0, 1, present state 0, next state 1. So here is present state 0 and the next state 1. You can see that J is 1 and K is again don't care. Next state is whenever present state is 1 and next state is 0, here with the red lines. So you can see that J is don't care, K is 1. And the rest, whenever present state is 1 and the next state is 0, we find J is don't care and K is 0. So this is how we can drive the excitation table. You just have to look into the characteristic table, you can find out the excitation table. And the excitation table you have to remember all the time when you are going to design the circuits with the help of flip-flops. T flip-flop, block diagram, T input, C input, Q and Q bar, two outputs. Its operation table, when T is 0 and we have assumed that the clock is active. Whenever T is 0, output is Q, that is store, no change. Whenever T is 1, output is complement. So with this concept, we can find out the characteristic table. So in the characteristic table, we have input as present state in the T, and the output is next state. Whenever T is 0, no change. Whenever T is 1, complement. So here T is 0, no change. T is 1, we have complemented. T is 0, no change. And T is 1, we have complemented. So here is the complement 1 to 0 and 0 to 1. We draw the K map. Here is the K map. And after solving this K map, we can find out the Qn plus 1 is equals to Qn bar T plus Qn T bar, and that is nothing but T XOR Qn. Now the excitation table, in the same manner, we can derive characteristic table, excitation table, and how it comes. Present state 0, next state 0, T is 0. Present state 0, next state 1, T is 1. Present state 1, next state 0, T is 1. Present state 1, next state 1, T is 0. So this is the way how the excitation table is drawn with the help of characteristic table. Now let us summarize all the excitation table in a single table. So we have present state and next state, 4 possible combination: 0 0, 0 1, 1 0, 1 1. And you have to remember, like SR equals to 0 1 0 cross, and write it in the reverse direction 0 1 0 cross. This is how you can find out the value of excitation inputs. In case of JK flip flop, you can write 0 1 cross cross. and write it in the reverse direction. 0, 1, cross, cross. For D flip-flop, D is equals to Qn plus 1. So 0, 1, 0, 1, it comes from Qn plus 1. And T is nothing but it is an XOR gate, 0, 1, 1, 0. T is the XOR of Qn and Qn plus 1. So if you remember the value of S, then you can find out the value of R, and same is true for the JK. You have to write down this a whole complete table in your notebook, then you can it will be easy for you to remember this. Now move to the problems in the level triggered flip flops, and the first very pretty much complicated problem is the race around condition that happens in the JK flip flop. The race around condition or race around problem occurs when both inputs of JK flip flop are 1. If the width of the clock pulse TP is too long, we are talking about here for the level triggered. The state of the flip flop will keep on changing from 0 to 1, 1 to 0, 0 to 1, and so on. And at the end of the clock pulse, its states will be uncertain. Suppose we are having J equals to K equals to 1, and whenever clock is active, so its value will change. Suppose it was 0, then the output will be 1. But after a certain time, it will again see that clock is active and we have J equals to K equals to 1. So what will happen? It will again change from 0 to 1, then 0, 1 to 0, 0 to 1. There will be glitches in the output. Now in the next slide, we are going to discuss with the help of the timing diagram. Now this condition of changing of state is known as race around condition. So in order to study race around condition, we have to clear some terms related to the clock pulse, and that we are going to discuss in this particular slide. So T is the time of the pulse whenever it is active, either 0 or 1. And delta T is the time it takes a flip-flop to execute the input condition. So here we see, here clock is 1, but J is 0, K is 0. So previous state was 0, the next state is 0. Now again, when we make J equals to 1 and K is 0, but because clock is 0. So what will happen? No change. So here is no change. Now again it see that clock is 1, J is 1 and K is 0. What will happen? It will change the value. It was 0, it will flip or toggle. So output will be 1. In this cycle, J goes 0, but K goes 1. But what happens? Whenever K is 1, it should be reset, but clock is deactivated. Clock is not active. So it will store the value. Whenever clock is 0, it will store the value. Now again, clock goes 1, J is 0 and K is 1. What will happen? It will reset. Now the value goes from 1 to 0. It will reset. Now this condition comes when J goes 0 to 1, but clock is deactivated because 0. So J is 1, K is 1, but it will store the previous value 0. Now the condition comes whenever clock is 1, J is 1, K is 1. What will happen? It will change value. It will change from 0 to 1. But it will see again after delta T times whenever signal is executed that again J is 0, J is 1, K is 1 and clock is 1. So it will again change its value. So it will happen whatever is the length or of the clock pulse, it will continuously change its value between 0 and 1. So it becomes very uncertain at the end of the clock pulse that we cannot find out the value, either it will be 0 or 1. So this condition is known as race around condition. Now to avoid this race around condition, what we do, either we use edge triggered flip flop because edge will come once and the duration of the transition will be very less. So either we use edge triggered flip flop or we may use master slave flip flops. So here comes in the next slide, that is the master slave flip flop. So what we use, What we do, we use two different flip-flops, JK or SR or T or D, whatever flip-flop we are using, and we construct a circuit in such a way that the first flip-flops acts as a master and the second flip-flop acts as a slave. So slave will always follow its master. So you can see directly that the feedback is from Q bar to J here and Q to K from here. It is Q to K. This is clock. So what we have used is we have used complementary clock. For the first clock, it is at level 1. It will be active at level 1. We have used an inverter. So here is, if it is clock, so it will, here will be clock bar. So whenever here is 1, here will be 0. So this flip flop will be deactivated. It will store its previous value, and the master flip flop will change its value accordingly. How many number of times the output is flipped between 0 1 and 1 0 whenever clock is 1 and J is 1 and K is 1. So it will never reflect at this particular output because this flip flop is deactivated. So whenever clock is 0, so here is 0, this flip flop will be deactivated and the output will be complementary. Either it will be 1 0 or 0 1. So slave will never feel a problem that it will have a 1 1 input. It will have either 0 1 and 1 0. So at the output, it will never change its output more than a once, because whenever it is 1 0, it will be a set condition. Whenever it is a 0 1, it will be a reset condition. So the slave will never face a problem that it has both inputs 1 1. So at the output, at the final output, we'll see that there is a single bit change or single time change in the output. Either it will go from 0 to 1 or 1 to 0. So the flicker, which is glitches which are introduced in the JK flip flop and J equals to K equals to 1 and clock is active, that may be removed with the help of the master slave flip flop. And another way to remove this race around condition that we can use edge triggered flip flops. Now we have two different types of inputs to a flip flop, that is known as asynchronous input or direct inputs. So here we have a D flip flop, JK flip flop, SR flip flop. This triangle here denotes that it is a positive edge trigger flip flop. Whenever there is a triangle, that is a edge triggered flip flop. So one asynchronous input is preset, another asynchronous input is clear. So here bubble shows that it is a negative level triggered, means whenever clear is 0, so here is it will be activated on 0 because a bubble is its input is inverted. So whenever clear is 0, that the out, irrespective of the input and the clock, output will be clear, that is Q is will be 0 and Q bar will be 1. Whenever preset will be 0, irrespective of the input, the output will be set, that is Q will be 1 and Q bar will be 1. And it should be kept in mind that never be preset and clear can never both be activated at the same time, because it will be contradictory in the circuit and the circuit may burn. So we can summarize that whenever clock is active, it is a positive edge triggered flip flop. It will act activated at the positive edge when the clock going from 0 to 1. Whenever clear is 0, output is clear, that is reset. Whenever preset is 0, output will be set. So we have the two different asynchronous inputs in all flip flops. So here in the same another example, I have put it bubble before the clock. So this triangle denotes that it is a edge triggered flip flop, and this bubble denotes that it is a negative edge flip flop. So here we can say this is a negative edge flip flop. So these are some representations of flip flops, how the block diagram of the flip flop is represented. Next is the conversion between different types of flip flops. So when we have we are given, suppose we are giving SR flip flop and we have to make T flip flop using SR flip flop, then we follow some steps and we can convert any flip flop into another flip flop with that given flip flop and some logic gates. So consider the characteristic table of the desired flip flop. So whichever flip flop you are going to design, write its characteristic table, and characteristic table shows that input and Qn is the input, Qn plus 1 is the output. That is the characteristic table. Fill the excitation values inputs of given flip-flop for each combination of the present state and the next state using excitation table. So here we use excitation table. So you have characteristic table in which you have present state and the next state. With the help of the present state and the next state, find out the excitation input of the given flip-flop, whichever flip-flop you are given with. Get the simplified expression for the each excitation input. If necessary, use K-map for simplification and draw the circuit diagram of the desired flip-flop according to the simplified expression using given flip-flop and necessary logic gate. And these steps will be pretty much clear when we are going to discuss it with the help of a example. Suppose we have to design a JK flip-flop using D flip-flop. So we have to design JK and D flip-flop is given. So we have to write down the characteristic table of the JK flip-flop like this. So JK and Q as input and Q n plus 1 is the output here. With 3 inputs, we have 8 combinations. So whatever table we have discussed will be here. So you see 0 0 store, 0 0 store, 0 1 reset, 1 0 two conditions set. So here it is wrongly written. It should be sorry, it will be set, and 1 1 it will be toggle, means 0 to 1 and 1 to 0. Now with the help of the excitation table of the D flip flop, find out the input combinations. So we have find out when a present state is 0, next state is 0, output is D is 0. Present state 1, next state 1, output is 1. So here is 1. Present state 0 0 0. Present state 0, next state 0. Present state 0 or 1, next state 0. So 0. So in this way, we find out the excitation inputs for the D flip flop. We solve the K-map for the D flip flop and find out the expression. It comes to be J D equals to J Qn bar plus K bar Qn, and we draw its circuit. We are giving D flip flop, and here is this total D flip flop is converted into the JK flip flop. So in this way, you can convert any flip flop to any another flip flop. So what you have to do, which flip flop you have to design, write its characteristic table. Then with the help of the excitation table, find out the excitation input, solve the K-map and draw the circuit. So let's stop today's lecture here. So if you people have